For my project, I decided to design a VTOL flying wing using 2D thrust vectoring, which I call Dreadwing. I used the traditional aircraft coordinate system without aligning the x-axis with the nose to avoid singularities and gimbal locks, since the aircraft hovers with its nose in the air. Here I define my orientation angles following the usual Euler angle definitions, where phi corresponds to roll, theta to pitch, and r to yaw rate. For the thrust vectoring mechanisms, I wanted to keep them as simple as possible to reduce parts count and aid with assembly. Each axis is controlled with its own independent servo and has linkages to push and pull each side to add more even loading. An important aspect of the design was to find a happy medium between deflection and resolution, to allow for a reliable control while also being able to deflect wide angles for large maneuvers. I'll give a quick overview of how I found my equations of motion. I started with Newton and Euler equations to find my forces and moments. I defined the motor yaw angle as mu, and the pitch angle as lambda, and the overall thrust force as delta. Using basic trig, I found the contributions of each motor based upon its pitch and yaw angles. Substituting and simplifying results in equations of motion for angular accelerations. I define the change in orientation angles and finally define my state vector as the two orientation angles phi and theta along with angular velocities. These equations are linearized around the hover condition and transformed into a state space representation for the simulation and control design. This state space model is found to be fully controllable, allowing full control over all states. Basic LQR gains results in all stable eigenvalues for the closed loop system. A quick overview of my simulation setup. I set up my sim to allow different trajectories and controller types, which is just between LQR and PID for now. I define my desired initial state of the vehicle and simulate using ODE 4.5. The LQR controller does a decent job of stabilizing the vehicle. At this point, I'm not too concerned with optimizing controllers for the sake of time. I can command a sinusoidal maneuver and also a yaw climb maneuver, which the controller handles quite well. Now for hardware. This is my own custom flight controller I have developed for my thesis research. This flight controller uses two teensies, one for input-output communication and the other for sensors, control law, and data logging. The board is MAVLink compatible and has onboard sensors. These onboard sensors include a GPS, barometer, IMU, and magnetometer. Here's my controller section of my flight controller teensy, which converts the sensor data and pilot controls and sends them into the controller class. Then the commands are pulled out and sent to the hardware teensy. My controller class is pretty basic. I find the error between the current states and the desired, then apply the appropriate gains. Something I discovered later was the need for scaling according to throttle, as the effectiveness of the controls change with the pilot's throttle input. I also make sure to clamp my control values as to not command a higher value than is physically obtainable. Here's the assembled vehicle. This setup isn't very pretty, but I was pretty much running out of time, so I was just focusing on getting something to work rather than focusing on aesthetics. Here's a basic hardware test, just to verify everything's working as expected. I'm also checking for control deflections and directions. This only has proportional gains applied currently just to make this process a little easier. Alright, now we can talk about actual flight tests. Tuning proved to be pretty difficult as accurate angle control was needed to even keep the vehicle in the air. Eventually the tuning gets better and I start to converge on better gains. Here I can get real-time telemetry data using my custom ground station, which helped in the tuning process. The tuning was still pretty difficult since I'm using a Cascade PID controller, so isolating the axes was more difficult. Eventually I get pretty close to the vehicle operating on its own. The roll axis is the hardest to tune as it has the biggest moment arm. The weather lately hasn't been the easiest to tune with, specifically with the wind. You can see here that I don't have the roll angle quite dialed in yet, But despite this, I'm still able to command values to overcome this error. Once I figure out this tuning, eventually I'd like to improve the gain scheduling with the thrust and add additional terms to my controlled state, including altitude and position tracking. In addition, I'd like to focus on transitioning between this hover mode and the traditional fixed-wing flying mode to allow the vehicle to perform more advanced missions.